Now these graphs have all been constructed geometrically, and none of these graphs has a scale, except if you decide to put a y-axis in your exponential function, then you the intersection of whichever exponential function with the y-axis gives you the point 0,1, whether it be this function in this point 0,1 or this function in this point 0,1. And that, of course, implies the entire scale of your y-axis. Okay, but it's not necessary to put the y-axis on there when you construct the graph. That can come later. Okay, well, we want to now look at some algebraic properties that are closely related to the geometric properties in ways we do want to explore in the course, and we did try to explore in the course. A power function has the form y equals f of x equals x to the p. I haven't stated it formally here, but if you have a constant y factor in the sense we've used it here, then you do have a function x to the p for some power p. And if you have a function x to the p for some power p, you do have a constant y factor. Every time x doubles, y will change by that factor. And we want to relate the y factor and the power. So the y factor is just f of 2x over f of x. Why is that? Because 2x, wherever x is, if x is here, then 2x lies twice as far here. And since this point is twice as far from the origin as this point, the y factor between here and here has to be the same as the y factor for all other pairs of points. And the y value at the point x is f of x. The y value at the point 2x is f of 2x. So that f of 2x divided by f of x is the factor by which y changes between here and here. And that has to be equal then, well, because if you plug in x to the p for, if the function is f of x equals x to the p, then f of 2x equals the quantity 2x raised to the p. Quantity 2x raised to the p is 2 to the p times x to the p. F of x is x to the p. X to the p divides out, leaving you 2 to the p. Now, you might not understand that from having heard it, but you've seen it. So if you don't understand it, go back and make sure you do. It follows from this, if the y factor is 2 to the p, it follows that p is the log of the y factor over the log of 2. Now, not everybody, most of the class was not yet familiar with logarithms and the laws of logarithms and the properties of logarithms. So the logarithm is just kind of this mysterious thing that I define just by this equivalence. So anytime you have a raised to the b equals c, that's equivalent to saying that b is the log of c divided by the log of a. You don't have to know any more than that to see that this is the case. Now you have to take my word for it that the log function does that. And to understand log functions, you really have to understand exponential functions, not the laws of exponents, okay? And you do have to understand exponential functions. Log functions are inverses of exponential functions. But, you know, that's something that we didn't completely build up in the course. We didn't really study the log function. And we're not really in a position at the level of this course to study the log function. Still, you can use this relationship with complete impunity. It works. And you'll see why later, if you haven't already. For an exponential function, the form is y equals f of x equals b to the x for your most basic exponential function. We do extend the term power function or exponential function to what we get if we multiply any of these functions by some constant number. But yeah, and you've seen that. You understand how that works. Okay, so if y equals f of x equals b to the x, and your doubling displacement, which is a little bit long to write into an equation, is represented by delta x sub d, change in x that doubles if you wish to read it that way, then we have f of x plus delta x sub d over f of x equals 2. Why? Because x sub x, x plus x sub d, if x is here, then x plus x sub d has to be a doubling displacement from that, so that the value at x plus x sub d has to be double the value at x. So when we do this ratio, you got to get 2. If you divide something that's doubled by the original value, you're going to get 2. That is algebraically simplified using the laws of exponents, which I keep reminding people they really need to understand because nobody really does. But I think some of you are getting there. At least were by the end of the course. Maybe you've got it by now. Using the laws of exponents, this simplifies if we plug into this function to b to the delta x sub d, b to the doubling displacement has to equal 2. And solving that, we just take the reciprocal delta x sub d power of both sides. We get b here. If you know the laws of exponents, you get b here. And you get 2 to the 1 over delta x sub d over here. Again, you really have to know laws of exponents. Everybody should know that by the time they're done with Algebra 1. Unfortunately, I find that few people do. SOL must not test it. And also, you could also solve this equation for delta x sub d. If you know b, you might want to find delta x sub d. So just using this fact here, we get delta x sub d as log 2 over log b. Now, just one comment on the sine function, which we didn't study in depth, but I'll leave you this comment right now. The period of the sine function is the change in x, whatever your variable is here. It could be t, could be theta, could be a lot of things. The change in this variable from the start to the end of a cycle. And I'll also just note quickly that we could take this graph and then slap another one on here and just keep going. You know, keep slapping copies of this cycle here and get cycle upon cycle upon cycle, an ongoing sine wave, which would correspond to we just keep going around and around and around the circle and never stop, at least not for a long time. Okay, the period is this. Okay, so there's the period. The thing we call the amplitude is just basically the radius of the circle that we started with, and that corresponds to the distance from the axis here up to the maximum point, or from the axis to the minimum point. If the period is 2 pi, and there are good reasons why the period of the basic sine function is taken to be 2 pi, it's because the analysis of the function is much simpler if the period corresponds to how many radii you've got as you go around the circle. Okay, and since the circumference of a circle is 2 pi times the radius, this becomes very useful. And it's the most useful measure of angle, the one for which the period of the sine function is 2 pi. And the measure of angle for which that occurs is called the radian, and that's something you really need to understand when you get to it. It's a little hard to get your head around because you're used to degrees, but the construction here didn't use degrees. You don't have to use degrees. You just take the period and call that distance 2 pi. And if the amplitude is 1, corresponding to a circle of radius 1, therefore to a graph that goes from -1 to 1, then that is a graph of y equals f of x equals sine of x. And you can start to explore the algebraic properties, which are, again, much easier to understand, and much easier to deal with, much easier to manipulate if you have that period of 2 pi.